Dr. Johan Vos and James Weaver, and you gave a talk yesterday about quantum computing. Now, I have to admit, I've given a few interviews before. By given, I mean I've interviewed people before about quantum computing, and I always feel a bit fuzzy on the details, which I suppose is part of the quantum nature of things.
Nice.
Thanks. It was a bad joke, wasn't it?
No, it's very good. It's very good. Yeah.
So, what is a qubit?
I can take that one.
Okay, yeah.
I'll take the easy ones. You take the hard ones. Okay.
Well, if you think a qubit is easy, then.
Well, okay. So a qubit is kind of like, this is probably a developer audience, right? So if you think of a classical bit, it can be on and off, on or off. A qubit is like that. It could be on or off, or it could be in some combination of states. They call it a superposition. That's neither on nor off. It's this state that really isn't even decided until it's measured, and then it collapses into either on or off. Kind of like Schrodinger's cat, the famous cat that when you open the box is either alive or not live. Yeah. And it can be used as the basis for some really nice computations, things that we can't do classically, like factor large prime numbers.
So, what about a qubit allows us to, I realize this is a very large question, what is it about a qubit that allows us to do that type of computation that would take an infinite amount of time, maybe, in classical computing?
Well, because a qubit can be in different states at the same moment, as Jim explained. It is on and off at the same moment. So 2 qubits, if you have 2 bits, for example, they can have 4 different combinations, but not at the same time. So if you want to evaluate those 2 bits, you need 4 function calls to evaluate all the different possibilities. But with 2 qubits, you have those 4 possibilities at the same moment, because if you bring them into superposition, they are 0 and 1 at the same moment with different probabilities if you measure them, but because they can contain the state, they can contain the information of all the bits combined at the same moment, you can do much more calculations simultaneously. In the end, of course, when you measure them, they will fall back to one state, but because all the computations can be done simultaneously, it's exponentially faster than if you would have to do them one by one.
I don't know if this is a philosophical question, but how do you do the calculations without measuring them?
So the trick with most quantum algorithms is leveraging the wave nature of quantum mechanics. And so there's a very famous experiment that probably everybody's heard of. It's called the double slit experiment, where they shoot photons through 2 slits, and they interact with each other in a wave pattern. And so you see a wave pattern then on the back wall where there has been constructive and destructive interference. And so leveraging the wave nature of quantum mechanics, quantum computing then can do, as Johan said, you can create combinations of qubits that are in different states, different phases, so that you can choreograph the solution. Then you can choreograph the state to where the correct answers will constructively interfere, and the incorrect answers will destructively interfere. So then you end up with if we're talking about the photon analogy, you end up then with a wave pattern that focuses light on one part of the screen, which is analogous to constructively interfering to get the correct answer.
And adding to that, in the end, of course, you still need to measure what you want to measure, but the answer to a difficult question can be very simple, and the calculations required to get a simple answer can be very, very complicated. So that is what you can do with quantum computing. The calculations can be extremely complicated, but then the answer might be very simple. The answer can be one number, for example.
The number 42, for example, yes.
And that's the answer to a very difficult question.
Yes, right, exactly. And so as Johan mentioned, it's you don't know the answer till you measure, and when you do measure, it's going to be some probability that that's the correct answer. Now with some algorithms, that probability can be 100%, like the Deutsch algorithm that we walked through yesterday. But with some algorithms like Shor's, or which factors large prime numbers, when you take that measurement, there's a chance, there's only a certain chance that that's the correct answer, and so it may not be, and then you check it, and maybe classically, using classical computation, you check that answer, is it right or not, and then you might have to measure again, and like run the problem again, maybe a few times, to verify that that was the right answer.
So you mentioned in your talk about, and just now, about quantum computing being leveraged to solve these very difficult computations and functions, specifically trapdoor functions like factoring large primes. So what are the implications on things like cryptography?
Yeah, well, cryptography is partially based on the fact that it's extremely hard to factor a large number into primes. So the moment that becomes very easy, one of the core fundamentals of the current encryption, for example RSA encryption, vanishes. So that means that it will become very easy to intercept encrypted communication and to break encryption, so to decrypt messages without having the right credentials to do so. And that's going to be a radical change. If someone can easily decrypt your message, then you can't rely on encryption anymore. So that will completely break encryption, but fortunately that does not mean that, it will break the current encryption, but fortunately quantum mechanics and quantum computing also allow for a new type of encryption that is based on quantum entanglement and so on. And that encryption cannot be broken by classical computing or quantum computing. So we should be safe for a while after we switch to quantum encryption. But once quantum computers are strong enough to break the current encryption, then the current encryption will be completely unreliable.
And you mentioned a really interesting piece of research done by a Chinese team to do with quantum encryption. So you mentioned quantum encryption. So could you tell me something about that?
Yeah, they've done a couple of experiments that were documented in the ArcSieve papers. One was where they shot a photon. Well, first of all, before they shot the photon, they did something called entangling it. So they can entangle two photons, and that's just a quantum property where you can entangle two subatomic particles, and so when you could separate them by a great distance if you want to, farther than light years or something. Just the other edge of the universe, doesn't matter. What they did is they shot one up to a satellite, and then they kept the other one on the ground. And so then they did the experiment where you measure one, and then measure the other one, and they're both the same. Because when you measure one in an entangled pair like that, then the other one collapses to the same state. And so they did one experiment from ground to the satellite, and then they did another one where they shot the photon from the satellite to the ground and verified quantum entanglement and in that context. That can also be used then, and maybe Johan would like to explain this, for something called quantum teleportation, to where you could teleport encryption keys.
Yes, well, quantum teleportation is it may sound a bit science fiction, and I have to disappoint the people who expect Scotty Beam Me Up happening soon, because it's not really like that already. Quantum teleportation allows you to send information from point A to point B without really sending the bit from point A to point B. So by sending, it can be shown, for example, that you can send the information of 2 bits by just sending 1 bit and an entangled qubit. So by leveraging entanglement and by doing applying gates to qubits, you can send the information from point A to point B without really sending the carrier of the information from point A to point B. So that sounds like teleportation, and it actually is teleportation, but it's not that. It's not really that you can. First of all, this works on a very small scale at high energies, so it's not that you can teleport a human from point A to point B, which does not mean that that is theoretically impossible. But not with this theory. This is about transferring information from point A to point B.
And then when you do that, then the information at point A collapses. So the information at point B is the only copy of it then at that point. Because there's something called no cloning. There's a no cloning theorem where you can't clone a quantum state.
Okay, so that's how it works for encryption then, because you have a uniquely shared secret.
Yeah, so that is indeed one of the core principles of quantum computing applied to encryption. If you have a private key and that has been tampered with, or if someone tried to read something private, then it can be detected that the message has already been read, because by observing something, it will fall back to the default state. And that is something that with some other quantum algorithm that you can detect. So if you get a message, and that message is supposed to be encrypted and only readable by you, you can relatively easily detect if someone else tried to read it, successful or not successful, and that means that someone tried to snoop your message. And that will allow much better than today to be sure that the message that you received is really not intercepted. So the moment that a hacker between 2 parties try to intercept your key and to break it, if you try to do that with quantum mechanics, you break the whole system, and it will be notified. So it's adding an additional security layer.
So we might lose standard encryption, but we'd have something much safer. Well, thank you both very much.
Absolutely.
You're welcome.